So good evening, everyone, and welcome back to the SSB Ground School. This is the series on that's more of a primary ground school, and the series is on the FAA's Glider Flying Handbook. And we don't teach the Glider Flying Handbook, chapter by chapter, word for word. We're not doing that, but we're following the topics that are in it and making sure that we cover a lot of those items that you may well get tested on or really need to know to fly a glider. So we have two CFIG candidates who will be giving the bulk of the presentations. There's one topic that in the weather that we're going to go through tonight that I kind of like. It's kind of fun. I'm a bit of a nerd about thermodynamics, and this one has a lot of thermodynamics in it. So I'm going to barge in and talk about it. But Jeff Clayton, he's a career aviator, was in the Air Force, flew primarily F-16. Also, he's a helicopter CFII. Casey Meeks, he flies just about everything that you can think of. If it flies, Casey has flown it. He's an airline pilot. He's got, I think, 4 of his own airplanes and 1 of his own glider. He likes aviation. He's a great aviator, and you'll enjoy hearing both Jeff and Casey talk about their areas of expertise here in weather. So, Jeff, you want to start off?
Sure. All right, have I got it down? You just see a big screen now?
Yep.
All right.
Things are moving
Okay.
well.
Yes, so as you talked about, Armin, we're going to be talking about soaring weather today, and I look at that as, understanding it, being able to predict it, and then assessing, how well you predicted it, how well someone else predicted it. We know there's a plethora of products out there that predict the weather, and soaring weather is no exception. There are a number of sites that you can go to, apps that you can have, even in flight. But understanding how the atmosphere works, and particularly how it applies to soaring, and particularly cross-country soaring, is really good. And then that'll help you make your own predictions or assess whether someone else's predictions are working for you. So with that, some of the topics, yes, I had to put a picture of one of my soaring flights in there. This is over the snowy mountains in Wyoming. The topics I'm going to cover are the atmosphere, and then because they are a big threat to any kind of aviation, but particularly glider pilots, because we're working amongst conditions that often result in thunderstorms. And then thermals, because the large proportion of the soaring, especially cross-country soaring, especially in the Rocky Mountain region where we are, but really all over the country and the world, is thermals. Even in places that primarily are ridge or wave, they're often using thermals to get to those, or get between ridges and so forth. So the atmosphere. The atmosphere can be thought of in terms of layers, but if you look at the diagram on the left there, you can see what those layers really are corresponding to is changes in temperature primarily. So it's broken down into the troposphere, stratosphere, mesosphere, thermosphere, and then actually also the exosphere. And then within that, we've all heard of the ozone layer. What I think is interesting about this particularly is that you get into the stratosphere and especially into the thermosphere, excuse me, and there are temperatures that are, warm type of temperatures, which I find pretty cool considering how thin the air is there. Also note on the diagram on the left, the tropopause, stratopause, and mesopause, and those are short, well, not so short, but regions of the atmosphere where there's a pause in the change in temperature. The diagram on the right there, again, it just is showing that obviously that's not to scale. If you were to put this to scale, I think the atmosphere would actually be, this magenta line would be about how thick it is. So the atmosphere is really, really quite thin. The other thing I want to mention on this is that where we're talking about weather, where we're talking particularly about soaring weather, but really any weather in our atmosphere, the vast majority of it's in the troposphere. You do sometimes get thunderheads that would go up into the stratosphere, but by and large, weather is a function that happens in the troposphere. So the composition properties of the atmosphere, you may already know that the atmosphere is about 78% nitrogen, 21% oxygen, and 1% other gases. And the important thing about this is that remains constant with altitude. It's always that same percentage. So, if you hear about someone having hypoxia, it's not because there's a lower percentage of oxygen. It's just there's less pressure of oxygen, and that's also, of course, horizontally. The thing that does change, and again, it's primarily in the almost entirely in the troposphere, is the water vapor content, and that is a big, obviously, part of what weather is. That's our clouds, our rain, humidity, so forth. On the diagram on the right, this really is showing that so nearly 100% of the atmosphere is below 164,000 feet. Okay, that's probably easy to digest, but 90% of it's below 53,000. So as we get lower and lower, it's more and more percentage. So kind of the important number for us is 50% of the mass, the density of the atmosphere is below 18,000 feet, and it's proportionally more and more as you get closer to sea level. So most of that gas, most of that water vapor is all down at the very lower regions of the atmosphere. Oh, and I do also want to say, not a backup, but most of the, or I should say the troposphere itself, that itself is somewhere around 50,000 feet at the equator in the summertime, and around 30,000 at the poles, and then in the wintertime that shrinks down. So it's a fairly narrow band of the atmosphere, which is already pretty narrow compared to the diameter of the Earth. Okay, so the meteorologists, geeks, came up with this International Standard Atmosphere, or ISA, that you may hear. So pressure and temperature is what we're referring to there at what's called mean sea level, so the average sea level. And at sea level, that is defined as 14.7 pounds per square inch, or 29.92 inches of mercury, or 1013.2 millibars of mercury. And then temperature wise, 59 degrees and 15 degrees Celsius. So that's kind of like the standard datum point for what they're considering a standard atmosphere. And you may already know this, that pressure altitude, and we did talk about this in earlier ground school, is defined with the altimeter at 29.92. In other words, sea level pressure. So that's going to, with that setting in, is going to be your pressure altitude. And then density altitude is just that corrected for non-standard. So that's the application of that international standard atmosphere. There's also a standard temperature lapse, or you could think of that as change or delta rate in the troposphere. And that is defined as 3.2 degrees Fahrenheit or 2 degrees centigrade per 1,000 feet. So it goes down by 3.5 degrees Fahrenheit for every 1,000 feet. And this is just a diagram. So the temperature that's defined as a linear decrease. So it just stays constant all the way up through the troposphere. Pressure, it's not linear. The pressure changes that you can see according to this diagram here, at sea level 1013 standard pressure. And as you get up in altitude, it decreases. Two pressures that roughly correspond to altitudes that you may want to keep in mind is 700 millibars is going to be roughly, again, it's going to change depending upon the day and the location, about 10,000 feet of altitude, and 500 millibars equates to about 18,000 feet of altitude. And density, that is going to change as a function of pressure and temperature, hence density altitude is being pressure altitude corrected for temperature. Someone have their mic on, might want to turn it off. So what makes the weather? It's really quite simple. It's the sun. Without the sun, we don't have any weather. So it comes from the differential heating, which is known as insolation, and then cooling, obviously late at night, like we are now, the Earth is cooling off, which results in large and small air circulation around the planet. So the large cells are, in different regions of around the globe, and then the smaller scale stuff is your high and low pressure systems and so forth, and then in extreme cases your hurricanes. And what changes the amount of sun that an area gets, which is what's causing the weather, is you have the seasonal variation, the tilt of the Earth. So of course in the northern hemisphere it's more direct in the summer, and in the southern hemisphere more direct in the winter. Your daily variation, sunrise to sunset, obviously, and surface differences, and this really plays into soaring when we're talking about thermals and such. The different types of terrain, whether it be just dark terrain or the angle to the sun, whether it's covered with vegetation, whether it's water, all that has differences on how much the sun is going to be absorbed. And then, of course, cloud cover. If it's a cloudy day, then virtually none of the sunlight gets through. And this little diagram here is just showing, the United States is a pretty small spot on the globe yet, but you could see that this insolation, this red area, is so much higher in the Southwest, and that's due to the drier climate and generally clearer skies. So even just over roughly the same areas on the globe, you can get large differences. And this other diagram here is just showing you, through the months, how much at different latitudes that sunlight changes. So if you're on the equator, it stays pretty constant. And then if you're at the northern latitudes, it changes hugely depending upon the month. So all that is going into how the sun heats the Earth, and the sun heating the Earth causes differential patterns in pressure and causes our weather. So the meteorologists or scientists break weather patterns down from big to small, at our big scale all the way up to 10,000 nautical miles, and in time, a year or more. We're looking at the general circulation, monsoon circulation, jet stream. I think of this more, and this is the macro scale, I think of this more as what we're talking about is climate, climatological regions and things. And then your meso scale is, decreasing down from a week to a day, and a day to an hour to minute. And we're talking about fronts and land and sea breezes, wave patterns, and even down to, thunderstorm size, large thunderstorms. And then, of us, is a special interest to us as glider pilots is on the micro scale. So a second or less to a minute, and less than a nautical mile. You might imagine that weather is, when you're talking climate, that's easier to predict, larger time frames and distances, larger scales of areas than the smaller areas. So no weather forecaster can tell you exactly where a thermal is going to pop up or when. And this is just a picture of that. So, our macro, we have these different cells and different wind patterns that set up, and they stay pretty consistent. Obviously, there are some changes, El Nino and La Nina weather patterns and such. In your meso scale here, you can see the variations in pressure, your high pressure areas, your low pressure areas, and your fronts and stuff. So we're talking about that scale. And then the micro would be, the smallest would probably be, a dust devil type of thing, or a small gust front. Okay, on to atmospheric stability, because this is kind of heart of soaring, or especially thermal soaring. So stability is, you could think of it the same way as you think of aerodynamic stability. So when we talk about dynamic stability, if something's unstable, it tends to want to continue to change. If it's stable, it tends to just come back to where it started in neutral. Is, well, if you give it a shove, it just keeps kind of going that way, but it doesn't accelerate in that direction. So you can think of it the same way with atmospheric stability. So the tendency for vertical movement, the rising or falling of a parcel of air. You'll hear that a lot. The easiest way for me to think of a parcel is the types of parcels that I try to use are thermals. So that could be considered a parcel of air, is this differential mass of air within the general atmosphere. So if the surrounding air, so the atmosphere in general, is cooling more quickly than that parcel, as that parcel goes up in altitude, then the atmosphere is considered unstable, and that parcel is going to want to continue to rise. It's going to have that instability, unstable. If the surrounding air cools more slowly than the parcel with altitude, then the atmosphere is stable. So that's going to make that parcel tend to sink. And then there's this term called conditional instability, and this is kind of big when we're talking about air going up over terrain, or a large air mass accelerating through a level of the atmosphere and creating a thunderstorm, just exploding into a thunderstorm. And so that's considered conditional. And then a parcel of rising air is considered to cool, and this isn't exact, but about 3 degrees centigrade or 5.4 degrees Fahrenheit per 1,000 feet until saturation, which is the dew point of that air. And that happens just due to the expansion of the air. So as it goes up in the atmosphere, as we showed earlier, the air pressure goes down, and the air is going to get cooler as it rises. And it's going to be roughly at that rate. There are things that change that, but at about 5.4 degrees Fahrenheit. Now, a standard atmosphere has a stable lapse rate. Remember, that's at 2 degrees centigrade per 1,000 feet. So the standard atmosphere model is actually a stable atmosphere. As we know, the atmosphere is often very unstable, so it's not standard. And here's a little diagram of this whole concept. An unstable atmosphere is going to accelerate. So you can just think of this as going to move. A stable atmosphere is going to want to just sit in a neutral atmosphere. This is really signifying sinking, and this would be sitting. And you can think of it from this cloud picture here, that the unstable is going to be rising, the stable is going to be sinking, and neutral is just going to be level. I mean, you really shouldn't think of it necessarily in terms of clouds themselves, but it's just a little picture there. And another way to think of it, and this is sort of representing a diagram that you can see when you're looking at weather prediction and forecasting models, and it's off of what's known as a skew T. But anyway, stable air, you could see, and we're going to get into this, what these mean, but dry adiabat and moist adiabat are going to cool off quicker than the general atmosphere. So as we were saying, a parcel of air is going to be cooling quicker. In an unstable atmosphere, though, either those moist or dry adiabats are going to cool slower than the general atmosphere. So it's going to be unstable. And then the conditionally unstable is just there in the middle. Again, just think of that as a kind of an explanational term, and not exactly what's happening with the atmosphere there. So since I just talked about it, here's some terms with atmospheric stability. The dry adiabatic lapse rate, and adiabatic refers to no heat loss, which is, again, it's not completely realistic from a thermodynamic standpoint. There's always mixing of the air of that parcel into other. So it's never going to be perfect where there's no heat loss, but for modeling purposes, for trying to determine what's generally happening, This is the way the scientists think of it. And that is the rate that the air will cool as it rises due to expansion, as I mentioned, with no heat transfer. And that's going to be at 3 degrees or 5.4 degrees Fahrenheit. Now, this other term, saturated adiabatic lapse rate, or SALR, is once that air is fully saturated, so now it's basically it's formed what we'd look and see as a cloud, it releases a lot of that heat. It now is going to decrease with temperature, or decreases temperature much less. Oops, I should say 1,000 here, not 100, but 1 degree centigrade per 1,000 feet. So it's a much slower rate than the dry adiabatic lapse rate. So once that parcel of air hits where it saturates, it's now going to cool at a much slower rate. And basically, that's what I'm saying here, is going to cool at the DALR until condensation occurs, and that's going to cool at SALR. So another phenomenon to be familiar with, especially as a soaring pilot, is a temperature inversion. So, you know, in the standard atmosphere and generally in the atmosphere, temperatures are going to decrease with altitude, but an inversion is where the temperature increases instead of decreases. And that area where, well, if there's a change, if there's a decrease and then suddenly there's an increase, that's known as a boundary layer. So that's the boundary between two very distinct layers of changes of the atmospheric cooling. It can occur at any level of the troposphere, but the one that you're going to see the most as a person on the ground, particularly, but as a pilot also, is a low-level inversion. And it's very common, most commonly caused by radiative cooling of the surface at night. So as nightfall happens, all the energy of the Earth is radiating back up into space, and it can cool the lower layers of the atmosphere, very close to the ground, much more quickly than the higher layers. And that's most likely going to happen on a calm, clear, dry night. So it's more common in the West than it is in the eastern areas or the equatorial regions. Low-level inversions, and we see them all the time here in Boulder, like almost daily, usually dissipate as the sun warms the surface, but it doesn't necessarily happen that way. Depending upon the atmospheric conditions, high pressure, terrain, things like that, snow on the ground, it can linger for days to weeks. When I was a pilot in Utah, we would get inversions that would set up, and the clouds would just layer there, and all the smoke and haze would just layer underneath you. You'd get down to IFR conditions sometimes for days, and it was pretty astounding, because you get above that level, you climb a mountain, and it's just clear blue sky above. Persistent high pressure, and that was the case there in Utah, and shallow cold fronts can also result in inversions. Another thing about inversions, that deeper inversions at higher levels will cap lift, for one thing, but also reduce the likelihood of thunderstorms. So if there's a pretty strong inversion at higher altitudes, even if there's a lot of convective activity, you won't get thunderstorms. So that's another effect of inversions further up in the atmosphere. So I talked briefly about a SKU-T, and this isn't a class on SKU-Ts, but if you do get used to looking at those, an inversion would look like this. So this red line here is basically the temperature, the actual temperature of the air in the atmosphere as it's rising. So up is rising, and left is cooler, and warm is to the right. And this, where it's actually warming as it goes up in the atmosphere, that's an inversion. And this is actually an actual screenshot that I took from a few days ago. And then as the day went on, so 4 hours later in the day, that inversion was gone. And that's very often the case, that you're going to have this low level inversion. Okay, so that's just kind of a brief talking about the atmosphere and stability and such. Go on to thunderstorms, because it's a very important part of soaring weather, is to understand why there are thunderstorms and when they're likely to exist. And and of course the hazards that have to do with them. So causes and prediction, there are three elements, and this is definitely something you want to be able to spit out to your examiner pilot, necessary for a thunderstorm: unstable air, a lifting action, and humidity. If you're missing any one of those things, you're not going to have a thunder, or if you don't have sufficient levels of those, I should say, you're not going to have a thunderstorm. So things that can bring these conditions, fronts, hot, humid, or even slightly humid lower atmosphere air with rapid cooling above. So if there's a large lapse rate and instability, rising terrain. You probably noticed that over the mountains is where you typically are going to see thunderstorms form first. So air pushing up over that rising terrain can give that lifting action, as well as fronts or the heating of the surface. So there's lots of things that can cause all those three elements to come together. So again, the meteorologist geeks have this thing they call convective available potential energy, or CAPE. It's a measure of the available energy in the atmosphere above the level of free convection, which is basically a level where the saturated air where the air has now become saturated in the atmosphere. And the important thing to us is it relates to thunderstorm occurrence probability and severity. So if you have a large CAPE, and especially if that CAPE extends well into the atmosphere, it's going to give a large probability of occurrence. And then the bigger number this CAPE is, the more severe those thunderstorms are likely to be. Another thing that as soaring pilots we want to be familiar with is the K index. And that is a measure of that lapse rate and moisture content in the lower atmosphere. So it's combining both the lapse rate that's happening and then how much moisture is in there. Again, those are two things that have to do with creation of thunderstorm. And again, they're going to give you an occurrence probability in that case. And a lifted index is a measure of the difference in parcel of air lifted and ambient air. So the difference in the temperature difference of that ambient air and lifted air at roughly the 18,000 foot level. And that's a indication of the severity probability of a thunderstorm. And here's just kind of the numbers associated with that. So if you have a 3,500 or more is extreme thunderstorm hazard there. This again is a skew-T diagram. So that level of free convection I was talking about is right there. So this is a thunderstorm that's basically forming almost at the surface. I have to imagine this is in the tropics or something. And the volume, or the area, I should say, of this is what the CAPE is. And my picture out of the way, you can see there's an extreme thunderstorm risk there. So it's kind of a picture on the model of what CAPE is. And there's also, you can see on there, there's a K index and a lifted index showing on there. So rapid thunderstorm development usually occurs when a CAPE is stored by a capping inversion is released when the lid is broken. So basically it's pushing up against this boundary here. And once it escapes that boundary, depending upon how the relationship between the actual atmosphere there and the saturated adiabatic cooling, that area in here is an indication of how much that energy is in the atmosphere. Here again, these products are easy to find with your K index, what your thunderstorm probability is, and then your lifted index, your chance of a severe thunderstorm. Thunderstorm life cycle. So, as we're flying around underneath these beautiful clouds, we want to have an idea of, well, is that developing into a thunderstorm? And if it is, well, what stage of the thunderstorm it is? How far away do I need to be? How soon is it going to turn into something nasty? So in your cumulus stage, mostly updrafts, rapid vertical development. So what you're going to see there is that columnocumulus. So you have all these puffy cumulus clouds, and then you have one that's just getting bigger and has more and more of that cauliflower look. that's the cumulus or growing stage, and it's going to be mostly just incredible lift. We talked about the possibility of cloud suck in one of the earlier briefings, and that would be the type of cloud that you would have that happen under, is that cumulus stage of a thunderstorm. The mature stage, you're going to have both strong updrafts and downdrafts. So this is where we're getting to severe turbulence. Tear gliders apart type of turbulence. And of course, rain, lightning, hail, wind shear, all the nasty stuff that we see, tornadoes from a thunderstorm. And the dissipating stage, now it's basically just everything coming down. So just, still tremendous rain. You start to, the shape of the thunderstorms falling apart. But you're still going to have of the lightning, you're still going to have the hail, you're still going to have all those dangerous parts of the mature, but it's on a decline. Really important, again, know some numbers when it comes to your examiner. The thunderstorm hazard is often exists well away from the storm itself. You can get lightning that shoots out the side of the clouds and then down. I've seen it personally before on the ground where a lightning bolt just comes seemingly out of the blue, and it's because it's traveling horizontally and then down. Hail can go downwind many, many miles from a thunderstorm. Your wind shear, you could be, again, miles away and have the wind shear and turbulence. It would behoove you, again, for purposes of your oral during your practical, to know some of the numbers associated with wind shear, hail distance, and so forth. And here are, speaking of some of the numbers that came out of the glider handbook, which I will say are different than some of the numbers I've seen in some of the other literature. 20 to 40 knots, these are typical. You're going to often see more than that. 5 to 10 minutes before diminishing, easily exceeds 60 knots. And then just more about the number, 50 miles away you can have from large thunderstorms. Okay, on to thermals, which is, like I said earlier, kind of the meat of what you want to know about as a soaring pilot, especially a cross-country soaring pilot.
Jeff, could I just chime in for one moment? The question that can come up quite a bit or can frequently come up on the oral exam is, how far do you have to stay away from a thunderstorm? And here's, there's like a lot of answers, but the FAA answer is 20 miles. So if you get asked how close can you get to a thunderstorm, the answer is not closer than 20 miles.
Or they might say, if there's two thunderstorms, how far apart do they need to be so you can go between them? Make you do something
complicated. Go on back.
Yeah, another one that I recall is wind shear. There's a lot, especially on the written, but even on the oral, they can throw out the 6,000 feet per minute downdrafts you can expect, and when are you going to have the maximum winds in a wind shear? So and you should know that wind shear can occur vertically and horizontally. It does occur vertically and horizontally. So it's bad stuff, especially in a glider. Okay, thermals. What are they and how do they form? So thermals are localized areas of surface heated air that rise into the atmosphere, and that's due to a process known as convection. And if you take a pot of water and you boil it, all that movement of the water in there, that's convection that's going on. And the same thing is happening in the atmosphere due to surface heating. So the handbook says typically 500 to 1,000 feet in diameter. I don't know. I think I've been in thermals that have been way less than that. And I also think I've been in thermals that have been way more than that. So I guess the way to think of it is they could be lots of different sizes, but most thermals are going to be, such that we can orbit in them or we can circle in them in a glider. It is important to realize that they're typically going to be smaller at the surface and they're going to expand in size as they go up. The more unstable the atmosphere and the greater the surface heating, more likely you're going to have thermals, and the stronger they're likely to be. kind of makes sense, hopefully, intuitively. It doesn't mean that they're necessarily going to be easier to fly in or smooth to fly in, or you're going to be able to stay in them, but that's generally true. Here in our area, 10 plus knots of these thermal strength are common. Even this time of year, just a few days ago, I was in 10 plus knot thermals. If you're on the East Coast or other regions of the country, much different story. And same thing on the size. So thermals can vary quite a bit, just on the topography and the geography that you're in. They may last only seconds, or to 30 plus minutes. They could just be feeling, like they're there all day kind of thing. Really important to understand, and this is just general with atmospheric instability, what goes up must come down. So that 10 plus knot thermal going up, there's likely some air that's coming down, if not at 10 knots, pretty close to it. So as that air goes up, there's cold air that's coming down, and that's helping push. It's a catalyst for pushing that air up. There's no free energy here. It's not like the air can just continue rising forevermore. There's a point where it comes back down. And so where we have thermals, we also have sink. And that's something we'll talk about when we talk about actual techniques. Thermals also require a trigger, and this kind of goes more into the theory. We talk more again about this when we talk about soaring techniques, but just because you have a hot day and an unstable atmosphere doesn't necessarily mean that you're going to all the time have thermals. It does take something to make those thermals want to displace. So speaking of thermals, there's different conceptual models of how they actually form and what they would look like if you could see them. And I think they're probably all have validity. So there's sometimes where it might be more of this column model. So where you have this area on the surface where this air gets sucked in as it's getting heated up. So it's pulling in this air around and it's going up in this column. And then at some point at the top, it starts to, as it cools, either you're going to have a cloud there or it's just going to cool enough due to all the mixing that you're going to, have a kind of a mushrooming out of that. And you can see in this diagram, it kind of shows all the turbulence and sink that you're going to have associated around a thermal. And it's just another view of that same thing on the side. And then there's the bubble model, which, the theory there is that when this breaks loose, it kind of closes up underneath, and it's just this bubble of air. And I think most pilots they've been soaring pilots that have flown for a while have, can validate this, where they've seen their buddy thermal in a way and they go underneath that area where they thought they were, where the thermal is, and they just can't find it. They're all going all over the place. They can't find it. It's because they're underneath that thermal. And you kind of get this is showing that cone shape, we're closer to the ground. It's narrower. Thermal cross section, I just threw this in there because I think it's important to understand, again, when we get into the technique of thermal, that it's not like it's a perfect circular shape, and it may even have often does have multiple cores. And then one thing that is generally true is that the strongest lift is going to be more in the center region of that, and hence why more of a bank angle is usually appropriate in a thermal. Thermal life cycle, just different things affect on the micro scale of the atmosphere, the amount of wind that's blowing, if shade comes over an area where the thermal had been, where there had been sunshine, the surface composition, whether it's facing the sun, whether it's rough, whether it's smooth. Lots of different factors affect the structure and the lifespan, how long that thermal is going to last. And really all this is showing is, how this thermal grows. And then at some point, even though we have what still may look like a pretty decent cloud, it's going to be primarily or entirely sink underneath. So on to kind of a, specialty type of thermal arrangements. And This is one I haven't seen here yet, and I think it's because you're going to have cloud streets more generally over flatter areas. Armin, you probably, when you were flying in Texas, saw cloud streets. They're more or less regularly spaced bands of cumulus clouds. They can extend for many, many miles, so they can be a very convenient way to make distance as a cross-country pilot. A field of cumulus clouds like streets where, like we see here, can extend for hundreds of miles. Don't know why, but the spacing between the streets is typically 3 times the height of the cloud. So the space between these is 3 times the height. So you can see these clouds are probably pretty close to the ground where this is. And they're aligned parallel to the wind direction. That's important if you're flying because you're going to make your best speed under the lift in that direction, but also realizing that if you go across the streets, that the wind is going to be blowing you from the side there. This is kind of more of a profile view of it. And they usually occur over land following a cold front with brisk winds increasing by 10 to 20 knots between the surface and the cloud base, and the wind direction remaining nearly constant. So it's kind of important that you don't have a shifting direction of the wind, or you won't get those regular streets. And there's a notable inversion or stable layer above it. So I guess you're not going to see a lot of thunderstorm development when you see streets, is what I would take away from that. And this kind of just showing the circulation pattern. So you can see if you're in between the street there, you're in the sink portion. And another, this I would love to encounter sometime, but a thermal wave. So that we talked about it, just talked about that inversion above the cloud street. If you have winds that go perpendicular, so now the winds shift from going this way, above the inversion going perpendicular to that, and increasing at 10 knots per 1,000 feet, 5,000 feet or more, cloud street waves can form in the stable air above, and you can actually be flying above the clouds in lift along this. Again, you'd want to, and that actually will be maybe a topic that Armin will cover, because it is a wave type of formation. So predicting thermals, like I said earlier, nobody's going to be able to predict exactly where the thermal is going to happen, but just in general of having an idea of what kind of likelihood of thermals and how strong they're going to be. The scientists and you as an individual can understanding the macro picture is your general climate. Seattle, Washington is going to have a much shorter season of thermals and going to have probably a lot more benign mellow thermals than an area like Boulder. So that's more the macro picture. Your meso picture, you're looking at, and this is, again, it's going to depend upon where you are. There's folks that have been here in the Boulder area forever that know, if there's a low pressure area here and a high pressure area here, that's good, conducive for thermal development, in the way that we want to work it along the front range. And it's going to just depend, like here in the Boulder area, prefrontal tends to be good. And other areas I've been in the country on the East Coast, post-frontal was the thing, post-cold front particularly. Obviously, cloud cover is going to affect. If you have complete cloud cover, it's going to really cut down on your chance of having good thermals. And then your micro, very specific what your wind directions and velocities are. So as you're hunting for thermals, knowing that wind direction and velocity, knowing where the sun's coming from, is going to really be a player in predicting those thermals. And again, we talked about the K index. There's also this thing called the thermal index, which is just a way to basically say the temperature between that parcel, the dry adiabatic rate of air rising, parcel of air rising versus the atmospheric. And if you have a big negative, that means that it's much more likely to rise. If you have a positive, it's going to be more of a stable situation. It's not going to rise. And finally, it's a good idea to know, it'd be nice even in first thing in the morning to know, hey, what do I expect cloud base to be? Is this going to be a good day to fly over the front range or not? So a very practical method of that for the above ground level of the cloud is to take your temperature in Fahrenheit subtract your dew point temperature, divide by 4.4 and multiply by 1,000. Or with centigrade, it's 2.5 degrees, or a factor of 2.5. The other method, which again, I'm not going to get into detail, but is to your skew T diagram will have what they call lifted condensation level. And you also can derive from that, although it's usually not listed on there, your convective condensation level. And I won't get into the details of what they are, but that's going to be where your clouds are going to be formed, is somewhere between or at one of those levels there. These are just a couple of videos. I didn't label what they are, but this is by our resident Bob Ferris, and it's a really good soaring weather, more of advanced degrees and different products and things that you can find on and interpretation of those products of soaring weather. And this is one here is by our own Armand, and this is about the skew T. So it's not a bad thing. You really will impress your examiner, especially if you're going for your private, if you can talk in any level of detail about the skew T diagram. And that wraps it up.
All right, Jeff, thanks. If you want, I can jump in here and do the wave, and then Casey, you can follow right after me with your topics on weather. So I'm going to go ahead and share my screen here. Go to the mountain wave. Sorry, folks. There is the button I'm looking for. Okay. So mountain wave is a really interesting weather phenomena that, and everybody can see my screen share, I hope. It says mountain wave. Is that right? You all seen it?
Yep.
Great. So at any rate, mountain wave is a very interesting phenomena, and it's something that wasn't really known about until two glider pilots discovered it in the 1930s. And it's a part of the phenomena that causes it. We have known about for, people have known about for a long time. They just didn't know it would cause that kind of lift and sink in the upper atmosphere. And, when I really kind of got interested in it and wanted to study it. And so I started to look at more of the scientific papers and data on it. And the scientists call it a gravity wave. And, I really struggled with that. Why on earth would they call it gravity wave? What's gravity got to do with this wave in the atmosphere? And it's also called lee wave. And I can understand lee because it happens on the lee side of a mountain. So that's easy to understand, but the gravity wave. And so I did a lot of thought about it and study, and so I thought I'd share what I kind of came up with on. So keep that in mind. So the conditions that favor this strong lee wave suitable for soaring is you have to have a mountain with a ridgeline that's perpendicular to wind direction. So think the Continental Divide going along the Front Range, north-south, and the dominant winds are out of the west. Mostly we get winds out of the west. So the ridge tops, the winds at the ridge top, in order to get wave, it's got to be more than 20 knots. You need a pretty good wind blowing along the ground to get this going. And that wind direction has to line up not exactly perpendicular to the ridge line, but certainly within 30 degrees of perpendicular. And the more perpendicular it is, the better the wave and the more uniform it is. You need a gradual increase in wind speed with altitude. And what that does is that forces the lower level air to wrap around the mountain. And we'll get into that a little bit more here in a moment. The wind direction also needs to be constant with increasing altitude. In other words, you can't have a lot of wind shear. It's got to be a pretty stable day with the wind blowing in the same direction as you go up, and then increasing as you increase in altitude. And you need a strong low altitude winds in a stable atmosphere to kind of keep things stable. So unlike thermals, this phenomena needs some stability in the atmosphere, although it needs to be blowing really fast, which doesn't sound as stable, but stable within that framework of fast moving air. So this illustration jumps into something that Jeff talked about. And so we see that this is showing wind blowing from the left side to the right side of the diagram. And the temperature is, I'm gonna see if I can get this. Spotlight going here. So down here we see that the temperature is 18 degrees C on the upwind side of the mountain. And the wind is blowing this way. It hits the mountain, and of course it's forced up. Well, when it's before there's a cloud that forms, the dry adiabatic lapse rate is 3 degrees C per 1,000 feet. And so it starts coming up here and the air starts to cool. Well, it gets cold enough to form a cloud. And that cloud we call the cap cloud. Well, once it gets into that cloud, as Jeff was saying, the saturated adiabatic lapse rate is less. So it doesn't cool as fast. So that means as the air continues to go up and into this cloud, the air here where it's saying 3 degrees, that's actually going to be warmer than the air over here that rose and wasn't, or it didn't rise, but stayed there and wasn't in the cloud. So remember the increasing wind speed as we go up, that kind of forces this air to wrap around. It starts coming down, but it only warms up. Now it's doing the opposite. The air is being forced down, so it warms adiabatically. And when it's saturated, it warms at 1.5 C per 1,000 degrees C per 1,000. But then once it gets out of the cloud, it warms at the higher rate of 3 degrees C per 1,000. So if you look at the two numbers on this, in this illustration, on the upwind side of the mountain, the wind is 18 degrees C. On the downwind side of the lee side of the mountain, the air is actually 4.5 degrees C higher for the same elevation. So what this phenomena does is this dumps a lot of warm air onto the lee side of the mountain. And here in Boulder, we call that the Chinook wind. It's known in the Western USA as the Chinook wind. There was a scientist by the name of Fern who actually discovered the phenomena. The scientists call this the Fern wind. But it's why in Boulder, we have some cold days, we'll get some snow, and then we go out, and then we'll go out one day and there's this warm wind, and you're like, gee, wind is usually cold, right? And it's coming off the mountain, but it's warm and it melts all the snow. And that's the effect of this. So what does that have to do with wave, you're asking? So here's just kind of another illustration of it, where you're seeing on the upslope side, you have colder air. It goes up into the cap cloud, it comes down the other side, and it's warmer. This is just an illustration that shows it a little warmer. So here's a picture of a cap cloud. I took this photo, I think 2 winters ago, And you can see that cap cloud. You can't see the continental divide because it's wrapped in that cap cloud. But that's what that cap cloud looks like. And you can see how nice and blue and clear the sky is above it, indicating pretty stable atmosphere above that cap cloud. And yeah, this was a day with a lot of wave. When the cap cloud comes down the lee side of the mountain, it's kind of interesting because we always think in terms of, especially with thermals or something, we think of air moving up, it cools, and then it becomes a cloud. Well, this is kind of the opposite that happens on the lee side of the mountain. So the air is coming down and it's warming. And so you get like these fingers of cloud that will stick down on the lee side of the mountain that has the Fern wind or Chinook wind going over it. And so it just gets smaller. Now, so, oops, I can't see this very well. So why do weather scientists call this phenomenon gravity wave? What does gravity have to do with the thermodynamics of the Fern wind? We observe that hot air rises, but surely hot air doesn't have anti-gravity. There's got to be something else going on. And it's the cold air. The cold air is denser and thus heavier than the warmer air. And the air that went over the top of the mountain stayed aloft is much colder, i.e. heavier, than the warm Fern wind that went down the lee side of the mountain. And this cold air mass is called the Fern Gap. And it's pulled down by gravity, forcing the warm air on the downwind surface upward. And then that air cools adiabatically as it rises, and the upward force is stronger than needed to create a stable lapse rate, causing cold air to get supercooled at the top of the wave. And then gravity causes that supercooled air to descend rapidly with adiabatic overheat, triggering a consecutive yet dissipating wave. So if we were to look at, that's maybe what something like a Fern Gap might look like. It's going to be very clear. There's going to be clouds on both sides. Here's an illustration where we're showing the Fern Gap. So all this cold air, let's see if I get this annotator going again here. Spotlight, here it is. So this area right here is called the Fern Gap. And so you have a lot of cold air right here where you've sent warmer air down this side of the mountain. You got cold air on top of it, pushing it down. Think of like a plunger or something, pushing it down. It can only go as far as the ground. And then it squirts up here and goes very high, much higher than the mountain. It overshoots. You get on this first wave, which is called the primary wave, there'll be a rotor at the bottom because you've got all this air moving up much faster than this air is moving. And it moves up. The rotor, if you're flying a glider, the rotor will be very rough, very violent, but you can climb up this side of the rotor, the upwind side of the rotor, because the air is moving up. So you'd fly it up. Sometimes you might find this type of cloud, which is called a lenticular cloud. And the air bends over where these lenticulars are. And then this air now is super cooled. It got sent up much higher than it should have just to cool adiabatically. So now it's going to fall very rapidly on this side, which of course causes this rotor to keep spinning. And then now it's overheated, so it zooms back up, does the same thing. There's a rotor down here. This second wave is called the secondary. It's also showing a lenticular at the top. Then the same thing happens. The wave happens. Now you've got all this super cold air up here. It drops. Then every wave after, and that wave can go downwind, 100 miles or more. And so the first wave is called the primary. It will be the biggest one. The second one will be called the secondary, and the third and all subsequent waves are called the tertiary. And the wave kind of dampens itself out over time, but it can go a long way downwind. This is just kind of, I think I already went through this, and that rotor at the bottom may or may not have a cloud, but the rotor will be there. So if you're flying your glider, expect to find that rotor. And the rotors do spin such that there's an upward side that's moving up, and you can actually climb in that. And if you get on the other side, you'll find the ground coming up rapidly. And the rotor is often very violent. It's the most, I don't know about thunderstorms, but it's a very violent encounter. And so, at any rate, here's kind of a depiction. I found this on the internet. I'm not sure if it's a real photo or if it's a drawing, but you can see here the cap cloud, and then what they call the Fern Gap. Notice there's a couple different ways to spell fern. That one may be the correct in the whatever language with a, I don't know what you call these over the O's, but it gets anglicized with FOE. Then there's this rotor cloud. These rotor clouds look like a long, thin cloud and a long roll, like a big Tootsie Roll in the sky. And I've been outside and looking at this phenomena, and you'll be out there and that, the wind on the ground is blowing 30 knots, and like up above, it's got to be going 40 or 50 knots. And that cloud just sits there. It doesn't move downwind. You'd think, why isn't this cloud moving downwind? And the reason is because it's spinning. So it's, you don't want to spin any longer than you have to in there. And then up high, you can see the lenticular cloud. And that lenticular cloud just forms because the air gets cold enough to form a cloud. And they're usually a fairly thin cloud, and they're lens-shaped, and that's what the lenticular denotes. Here's an actual picture that I took in my backyard, and you can see the cap cloud over the continental divide, and you can see these long, thin rotor clouds. This cloud up here, I don't know if hopefully you can see my pointer. It's up pretty high, it looks pretty thin. That's probably a lenticular. And you can get a better view of this lenticular here. But you can see these rotor clouds, and you can see that they are in sequence. So here's like a line of rotor clouds. That's probably a secondary. And then this is a tertiary line of rotor cloud. Here's a picture a little further away from the mountains. You can see the cap cloud back there. There's a rotor cloud, I think much closer probably for the primary. This one's probably for the secondary. This row here is probably for the tertiary. More pictures, and as you can see, this first rotor cloud here is pretty well defined, whereas this one's getting a little wild. So, and then you can really see the lenticular cloud up over the top, and the rest of the sky is blue, indicating some stability. This is a picture of some lenticulars, and I'm not sure if this photo is really of lines, but it gives the idea that wave can run downstream a long way. So that's kind of my overview on wave, and I love that phenomena because there's just so much thermodynamics in it. It's such an interesting. So this winter, when you're outside in Boulder and you feel it warm, and you go, wow, how can it be so warm here in February? And that wind just warms you right up. And that's why it's the Chinook wind doing that very interesting thermodynamic phenomena. So with that, turn it over to Casey, and Casey can give us his presentation on the rest of the weather that's in the glider flying handbook.
Thanks, Amon. And thank you, Jeff. Those are some huge topics. Again, I'm glad we split this one up because this is a massive topic. I think we've pretty much followed the same format in the glider flying handbook. So Jeff started out with the beginning. The middle portion is representative of a wave. Great job, Armand. That's a great concept for us to understand, and something that's actually going to be starting for us really soon. It's wave flying season kind of starting now. So we'll get to see a lot more of that coming up. Where I'm going to pick up is on page 914, and we jump back to some other soaring concepts and weather associated with different types of flying. And the first one that the glider flying handbook is slope soaring. So Jeff was able to talk about thermal soaring, Armand talked about wave soaring, and then slope soaring. Slope soaring is probably the oldest form of glider flying. Lilienthal in the very beginning, and even the Wright brothers flying in Kitty Hawk were really using slope soaring to get their feet off the ground the first time. Slope soaring, also known as ridge soaring, is simply lift produced by the mechanical lifting of air moving up a slope. And this is a great visualization. If we think about a mountain here, we see that there's good lift as we push up against the hill there, and then there's a lift zone. This lift zone typically will extend slightly above the ridge, but not too far. Let me get to my next slide here. There we go. So the best ridges are typically a few miles long. We don't typically get good ridge lift off of a single mountain. If we think of a mountain back behind Boulder, like Sugarloaf, that looks more like a peak or like a cone, that's typically not a good geographic formation to be able to create ridge lift, because the air will simply move around it'll move around instead of up over the top of that feature. So typically something a few miles long is good. Slope lift can extend to a maximum of 2 or 3 times the ridge height. Typically, once you get maybe 500 feet, 1,000 feet over something, you'll start to see that decreases significantly. An ideal slope that we want to see is something on the order of 1 to 4, something that climbs a foot for every 4 foot horizontally. So sometimes a cliff is not the best formation for lift. Sometimes something like that figure A would be much better for us, because it would give the opportunity for that air to rise smoothly without a lot of turbulence forming on that. A great example that we have available in Boulder is the Flatirons, and the Flatirons is such a cool place to go play in ridge lift because it's relatively consistent. You can see there, though, there's a lot of gaps in the terrain there that can create a lot of eddies and some other things. But it is a great place to have ridge lift. Keep in mind, too, at the glider speeds that we fly at, even at min sync, we're flying relatively quickly. So a big, long ridge that's several thousand feet high is going to produce our best terrain for slope soaring. I fly paragliders here a lot, too, and you're flying at a much slower speed, and the effect of that ridge lift is a lot easier to tell when you're flying slower. However, please keep in mind that you can find sink on the downwind side of the slope, as we see there on figure A. I think that's actually a little over dramatized. I mean, there definitely will be sink on the backside, but depending on the stability of the air, that sink might start to actually create a wave formation and start to climb again some distance downwind. An interesting phenomenon that the glider pilot handbook doesn't talk about, but can become apparent, is something called lee side thermals. And Jeff talked about thermals and having the ingredients for thermal. And sometimes wind flowing down a ridge, especially if there's sun on the backside of the ridge, can actually trigger thermals on the backside as well. And that can mix with that ridge lift. So a lot of times you might find yourself in ridge lift, and then you might be able to connect with a thermal and continue to climb. And that's typically either a front side or a lee side thermal that you've been able to connect with. Wind speed typically needs to be 10 to 15 knots to create enough dynamic soaring to be able to move it over to the top. In figure B there, we see what might happen on something like a flat top. You might find this up in northwestern Colorado, up over the big flat tops there. There can be good lift on the front side of that, but typically a big rotor sitting over the top. And then figure C there is maybe a great indication of what might happen if you get too close to the flat irons there, that each one of those steps can create an eddy and can create turbulence. So very important to give yourself plenty of distance when flying in ridge lift. Another important concept, and this is from Helmut Reichmann, an old book from cross country soaring in 1978, but I think this is one of the best illustrations of how you can expect the lift to actually move forward on a slope tangential to the face. So we typically find the best lift below the ridge within a few hundred feet of the ridge, but then above the ridge, we actually want to start making our way out in front at an angle, and we'll find the best ridge lift there. If we move ourselves into this position, expecting better lift, you'll actually find that you'll encounter that sink zone. And then of course, keep in mind that this is an idealized figure. This is a perfect shape, but any uneven slope with ledges or steps will cause turbulence, eddies, and sink. Another type of lift that you need to be familiar with is something called convergence lift. And convergence lift is caused simply when two opposing air masses meet. This is really common in coastal areas. In this case, we see that during the daytime, we get inland heating. This happens a lot, especially in the California area. That's a great example. If anyone's had the opportunity to go fly Torrey Pines or any of the inland sites there in a glider or paraglider or hang glider, that's very common. You've got mountains and deserts back there, and they warm really rapidly with the morning sun. And then, of course, we have cool sea air rushing in and creating a natural cycle there. Where these two air masses meet, though, that's a very common coastal sea breeze, we call it, or maybe even a mini cold front. And that can create some fantastic lift and is typically marked by a curtain cloud, which we'll talk about here in just a moment. But very consistent lift that happens typically on coastal areas, but can happen here even in Boulder too. Keep in mind that this front moves from time to time. If this warmer air is stronger from the desert side, it can actually push this out over the sea. Or if the sea breeze is particularly strong that day, that can push that convergence line, we call it, much deeper inland. So the position of that can change significantly day to day and can actually move throughout the day as well. So important to understand that that convergence line may move. If you find yourself on this side of the convergence line, it's actually very cool and stable air, and that can actually what we call scrub the whole area of thermals. So it can take away one of those ingredients that we need for thermal formation, which would be heating, and can make it so it can be very, very difficult for thermals to form in this area. So something to keep in mind, and that will also be marked by very clear skies over that area. This is a picture from one of Clement's video, and I highly recommend you take a look at this video. It's again available on his webpage, and the name of this is Extreme Final Glide. And this is a great indication of actually convergence forming here over the Boulder area and what's called the curtain cloud. So a curtain cloud is really just that. It looks like you pulled a curtain down over the cloud. And we can see that there are two air masses here that meet, maybe much drier air coming from the west and more moist or more humid air coming from the east. And those two are colliding. If we find ourselves in this convergence area, and you can see this even happened in the wintertime, we can see the lakes are frozen down there and snow on the peaks over there by the ski area. But easy to fly hundreds and hundreds of miles in a very straight line here because it's very consistent lift that's associated by this convergence line. Very cool. One of the things that we want to talk about, and the last part of the handbook discusses, is forecasting and forecasting tools. And Jeff did a great job of describing sort of what the general weather patterns need to be, and how moisture affects that, and of course how that takes us into cloud formation and even wave formation. But there's some things that we can do and some suggestions for planning. So one of the things that is really good for just planning days ahead is to take a look at just general weather patterns. And we can get to that through the National Weather Service. It's a free service. And we can look at lots of different types of forecasts here, local forecasts and even aviation forecasts. When we come to the aviation side, this takes us to Aviation Weather Center. And this is really the best place for free and government sourced aviation weather here. We can see obviously METARs here, which is our current weather forecast, our terminal aerodrome forecast here, PIREP signets, and other things. We do also get some very generalized weather maps from these tools, but a very good free service that we want to take a look at, maybe when we're many days ahead to understand the general weather patterns. So that's something that we would want to look at maybe the night before to understand general weather forecasts much closer in within about 24 hours. And something else that is a paid product but is very, very effective is ForeFlight. I don't know, it's interesting coming from general aviation and seeing the forecasting tools that everyone uses, but I think this is a great tool. It is a paid tool, but it really takes all of those government forecasts and puts it into one place. The great thing about ForeFlight as well is it provides something that you can put on your iPad and you can pull up those forecasts as well. As Jeff said, it's important to understand some of the general weather patterns that are happening at the time. So this is our current basically forecast chart or prog chart. And it basically shows that today we've got a high pressure building, but we've got a trough that just passed us. So really taking a close look at this, we can expect increasing winds that will be flowing into that trough associated with that over the next few days. Another great tool here is the ability to quickly pull up a forecast and a METAR. Typically in Boulder here, I use Jeffco as our best forecasting point here, so we can see the current weather at Rocky Mountain Metro. It used to be called Jeffco, and then of course we can pull up the TAF. The TAF is our forecast for this airport. It typically covers just about a 24-hour period, and we can quickly see here that we expect VFR conditions and a little bit of light south winds moving into the area. Another forecasting product that we have available through this is the MOS. The MOS is a similar forecasting model, but typically takes us out several more days than the TAF will. So typically we get 2 to 3 days of forecasting here, which is great. And something that I highly recommend to everybody here is to start reading the daily area forecast discussion. If you want to learn about weather and you want to understand what these gentlemen have talked about tonight, especially on the mesoscale of the weather, this is a really fantastic tool. You'll learn a lot of the language associated with forecasting, and just an absolutely fantastic tool. We can see short-term and long-term too. So this is really useful when it comes to planning. Something else that we want to be familiar with when we're preparing for our check ride is the available government-produced charts, weather charts. A lot of these charts have really changed over the years. And in fact, there's several forecast products that are discussed in the Glider Flying Handbook that simply don't exist anymore. But you'll typically find this either in Aviation Weather Center, or you can find it through ForeFlight. But we can see forecasts of flight category, our latest surface analysis, which is really helpful. And then of course, some of our forecast products that show areas of rain, thunderstorm, precipitation coming up over the next few days. Also, our prog charts are very important. These are government produced charts that indicate what we can expect really throughout the entire nation as far as frontal boundaries, high pressures, low pressures, and the likely chance of rain several days out. So really some fantastic things that we want to look at. Obviously, as Jeff talked about, we want to think about stability. Stability is typically illustrated to us in terms of convective outlooks. So if we see, something that shows a high chance of thunderstorms or marginal VFR, we can really infer from that whether it's going to be an unstable or a stable day as well. And then, of course, we also have convective forecasts. This is a time of year that we get into relatively low convectivity because we're cooling so rapidly, especially in this part of the country. Surface analysis charts, obviously very important, and that's something that we probably want to be looking at on a daily basis to understand the areas of circulation. Keep in mind too that in the northern hemisphere, we will get a clockwise flow around a high, and we'll get a counterclockwise flow around a low. So we can see where those two areas meet. We'll typically get frontogenesis, or the beginning of a front, or convergence, which can take place either in a warm front or a cold front, and can create severe weather for us as we're looking ahead. There's lots of different weather products available. One of the important things as a soaring pilot understands is the winds and temperature aloft forecast. That's a product that's called FB, and it's a 12-hour forecast that's issued at 00Z and 12Z daily. Keep in mind right now we subtract 6 from that to get our time frame. So about 6 p.m. and 6 a.m. Is when we'll get those products forecast and available to us. This is a graphical depiction of those winds and temperature aloft forecasts, and we can generally see today that we're expecting zonal wind. Zonal wind just means from west to east, or kind of a standard wind flow for our area, and relatively strong winds to our northwest. We can also see winds and temperature data in a graphical format. In this case, over Denver, we can see different winds and temperatures at our different levels. Keep in mind that any altitude above flight level 240, it automatically assumes that those temperatures are going to be negative throughout the stratosphere, as Jeff indicated, that we typically are going to have a decrease in temperature. This is a much broader scale forecast. This isn't nearly as detailed as what we might find in the T-skew diagram, but something that helps us understand what might be available in the next 12-hour cycle. One of the tools that I really like too, and Jeff indicated what we would use through a lifted index or in the K index. And again, lifted index, those negative numbers indicate that we're going to have strong lift, which could lead to strong thunderstorm potential. And then our K index as well. And a place that we can actually find that is through the National Weather Service. And they actually have a soaring product here that's available, again, a free product, and that's called the Soaring Forecast. So this is our forecast for tomorrow. I just pulled this up, and it says it's actually good. Usually it says excellent there in the summertime, but we might expect maximum rate of lift of 797 feet a minute with a maximum thermal height of just over 14,000 feet. That's I think a lot of people debate whether this is useful, but I actually find that this is a great place to start if I'm considering flying, just to understand whether or not it might be a good day to reserve a glider and head out. One of those, the great things about this product though, is it does give us our lifted index and our K index there, and that can be relatively hard to find on some other government products there. Through this too, we also see our basically our winds and temperature aloft too. And this is the data that is typically used to build a T-skew chart. The T-skew charts are very interesting. Those are created through soundings typically. So a sounding is when a forecaster actually deploys a balloon with a packet and it goes up through the atmosphere to capture these winds and temperatures aloft to create those, to sample the air and to create those forecasts. However, a lot of them, there's only a few places now in the country where they do those. So a lot of these are mathematical and theoretical, and they get that data from other places as well. But I kind of like to start here with our soaring forecast, and that's a great place to find those K index and the lifted index. Cool. So day of planning. So there's some really great tools as we get ready to launch for a day that can really give us some very detailed information. One of those is the Black Forest RASP. That's a regional atmosphering and soaring prediction. This is, I think, Armand actually put together by our friends down at Black Forest, this particular website. And this is using RASP data to give us some very detailed information, things like thermal updraft and BS ratio. I love that term, BS ratio. What that really stands for is buoyancy against shear. So it doesn't necessarily mean that we're going to encounter BS on this flight, but anything with a high buoyancy to shear ratio means that those thermals might get kind of broken up. It can be very difficult to fly in some of those things. Our updraft velocity, the top of the lift, boundary layer top, and the depth, and thermaling height. So some really great products available here that are free. All things in aviation, especially in soaring. There's some really great tools that are available to us that are paid products. Another paid product that you might want to become familiar with is called SkySight. I actually hadn't used SkySight before I came to flying sailplanes. I always used a product called XC Skies as a paraglider pilot. But this is a really neat product that really takes all of that data and helps put it in a very clear and concise way to be able to understand very quickly whether it could be a good soaring day or not. So we can move through the day and we can see tomorrow actually looks better if we were to head north. Better, higher potential flight distance is what I'm typically looking at there. XC speed is an indication of how fast we might be able to fly in that area. Something that's really neat is a forecasting tool. It's a bit of a theoretical tool, but we could actually drop a spot here and ask us to sort of tell us, if we started here in Boulder, what might be a potential task that we might be able to fly. And that's really fun to take a look at and understand what the computer thinks we might be able to fly. And what you'll typically see if you do this on a daily side is this will keep you in areas of obviously the highest thermals and away from thunderstorms. Some of the other products we can see here are height of thermals, or depth of thermals, and also significant weather. So a really great forecasting tool, but relatively expensive. I guess not compared to all things. But something that is really fun to play with and go fly on a day and see what people do. Something else that can be done is you can actually download someone's flight from a day and overlay it over the top of this chart as well to see some of those different products. As a takeaway from this, I think what you really want to do as you're preparing for your check right here is just to understand that there are a lot of government products available, but also a lot of private products that help us understand what the available soaring weather is. And as we go through that day to day to day, I encourage you to take a look at the sky and understand what you're seeing, whether you're seeing wave formation, thermal formation, if it's overcast because we're in a low pressure, if there's a cold front approaching, or if we're centered in a high pressure, and how that affects our opportunities to soar through all these different soaring mechanisms that we've talked about today, whether it's thermal soaring, wave soaring, convergence, or just simple mechanical lifting and ridge lift. So quick summary there, but Armand, thanks for giving me the opportunity to kind of summarize what that looks like at the end of such a long chapter.
All right, Casey, thanks. If you want, you can release the screen. Yeah. Okay, we've got several students here. We covered a lot of material, but there's a lot of weather in aviation and an awful lot of it in soaring. So Eric, Michaela, Danny, Johan, you all, anything you want to ask the Jeff or Casey or even me?
I have a quick question. So when you're reading I forgot what they're called, but like the reports for the weather, like I'm not 100% sure, like really good on reading them. Do you have any like good tip? I don't know. Like, do you have any good tips on trying to figure out how to understand it? I'm sorry. That's a really odd question.
Michaela, that's a fantastic question, and I'll let Armand follow up, but I think it really comes through observation and understand what those resources are. If you start with NOAA and just go look at those weather charts and then look outside. So whether you're flying that day or not, try to understand what you're feeling, and even keeping a diary can be a really great way to start to put those pieces together. And that's a really valid question. I mean, you're talking to people who have spent their entire lives trying to figure this out, and it's something that's really hard to grasp and understand. But from a big scale, if you start keeping a diary and looking at some of those resources that we talked about, I think you'll start to quickly put those together and understand the best way to do that. There's also really great primers if you simply Google things like how to read a T-skew. There's lots of great articles that really simplify that and can help break that down into something that's usable. And then if you keep a diary when you go fly, download the T-SKU, download the forecast, the METAR and the TAF. And then what are your observations? What was it like when you flew? And what did you experience? Was it a smooth day, a rough day, strong thermals, lots of wind, lots of shear? And I think you'll start to put those points together really quickly. Armand, anything to add to that?
You know, weather, studying weather and forecasting weather is a science. And like most sciences, it's not, there's an awful lot of information. There's an awful lot to consider. There's a lot to learn. So, I mean, it's not like it's something where you can read one page and go, oh, I get it. I know how to forecast weather. It's a lifelong pursuit, and it's really fun and it's really interesting. And the more you learn about weather and the more you, and just like Casey says, you go out and observe it. And, whether you're in an aircraft or you're just standing in your backyard and observing it, there's a lot to observe, and you can look at things like, if you look at the weather and it says there's a front coming through, well, okay, we'll start observing. Okay, what does that mean? Does it mean like all of a sudden the wind picks up, the wind shifts when it comes through? So Michaela, there's just there's a lot to learn. It's not something you should expect to learn in the next 14 days. I mean, it's a lifelong learning thing. And there's a lot to weather, and you'll learn things, and then you can go out and observe what was in the forecast and say, yeah, just like on a wave day, you can go out and observe, yeah, it really is warm. It's like 65 degrees today, and yesterday it was 20. What happened? And then, after the Chinook wind ends, it goes back to 20. And you can observe that. Or, you can look up and you can see those rotor clouds and seeing them, and knowing that the wind just about blows you over while you're standing out there, but the cloud isn't moving. So you realize, well, that cloud's rotating. And you can see the lenticular clouds, and you can see them up and down the Front Range, and you know what they are. Or you can watch a thunderstorm build up and just kind of watch how it blows up. You can see that in the atmosphere. So, look at it as a lifelong learning thing and an observation thing. Don't look at it as like, wow, this is really overwhelming and I can't learn it in 30 days. So, I'll just have to, forget about it. No, you don't have to forget about it. Just learn what you can as you can, and consider it a lifelong pursuit, not a.
Hey, if I could add my two cents also, Michaela, is it's not generally done with glider, but there's no reason you couldn't, but is to get what they call a standard weather briefing, because those are the experts. And especially if you ask questions, they'll probably love that, because there's not too many people that do the telephone, hey, can I get a standard weather briefing? You would have to basically say, hey, I'm going to be flying such and such aircraft, so have your instructor help you through it to come up with a simulated flight. And I know at the school I went to for helicopter training, most of the students didn't want to do it. They just wanted to do it on ForeFlight and get but if you have someone brief you, and in the Air Force, we used to have to do this, they'll take you through all those charts and all those tables. And if you ask questions, they'll be happy to provide that. So they can kind of tutorial you through some of those products. So just another way to kind of have the experts give you a real world, real situation. Here's how they flow through all the charts, especially if you do ask questions.
And let me throw in an FAA question here, FAA question and answer. So where are you supposed, and I'd like to have Danny or Michaela or Johan or Eric answer this question. Where do you go to do that phone call to get the weather briefing? What number do you call? Any of the
100 WX brief.
There you go. Very good.
And that's 1-800-WX-BRIEF. There's actually a website now, 1-800-WXBRIEF.com. You can set up an account on it. And what I think is a good drill for students, even for experienced pilots, is when you get up in the morning, even if you have no plans at all to fly that day, say, well, I think I'm going to look out and see if I can fly. You do go through the weather briefing process and then just watch and see what happens in that night, then review, well, did what I think was going to happen actually happen? And I did want to add in one other thing. I don't know if, it's probably beyond for the students, but I know in one of the briefing earlier, which were quite good, by the way, I heard some discussion of sea breeze, and I live in Florida. And I don't know if you guys are curious, but I've flown in the sea breeze down here. It's an interesting weather phenomenon because we have a peninsula. And during the day, at the beginning of the day, the peninsula heats up and starts forming basically lines. It's like a cold front on each side of the state, like a line of weather, which is sucking in the cooler air from the oceans. And these fronts, sea breeze fronts is what we call them here, will start migrating in toward the middle of the state as the heat continues. And some days they might meet in the middle, like late in the day. Some days they'll meet closer to one, the Gulf side or the Atlantic side. But if you get up in a glider in those things and get on the edge of them, you can go for miles and miles and miles. It's kind of cool. I remember being under one, and I couldn't go up any higher because it was clouds above me, but I was just accelerating just in a straight line. So a lot of fun.
Yeah. So there's, weather is a lot of learning. It's a lot of observation. And, the more you learn, the more you observe. The more you observe, the more you learn. The more you learn, the more you observe. And you just got to figure you're just going to keep doing it for years and years and decades. And there's always something new. There's always something new to learn and get better at weather forecasting. It's kind of fun, and it affects you, even if you don't fly, obviously. So it's a good thing to do. Anything else to discuss? All right. Well, if not, then we'll go ahead and conclude this section or this part of the series of Glider Flying Handbook. Thanks especially to Jeff and Casey for putting on such great presentations. I chimed in on this one because I just really like the subject and couldn't resist. But anyway, thanks. And next week we'll probably have the last in this series of the Glider Flying Handbook series, where we're going to talk about cross country and flying cross country, and we'll probably do a little bit of height circles. We'll add that in. I'm not sure if that's in the Glider Flying Handbook or not, but it will be on oral exams for private and commercial glider add-ons, and so we'll get that covered. What am I missing? We're going to do cross country and what else next week?
I think it's kind of the same soaring techniques, I think, and cross country, which we can kind of meld together. They're really one and the same, right?
Yeah, they kind of are. I don't know how you separate them, but
anyway, we want to do, there's also human factors. I don't know how much you want to talk about that.
Didn't we do human factors on the emergency procedures?
Well, there's certainly some overlap.
Yeah.
There's some things on human factors, and I don't know how much, because it's PTS versus ACS with the glider. Not that really should make a difference, but there's aeronautical decision making and all the little things that go with that. 4Ps, and there's things that could be talked about. I don't think it's as relevant to glider flying a lot of time. Aeronautical decision making is, but a lot of the other topics, I think,
Yeah, and maybe we'll add in something about the dangerous attitudes. Have you studied it? I think that dangerous attitudes thing is really interesting. The FAA, I guess, put that together in the 1970s and realized that there are 6. I mean, everybody has to some degree these dangerous attitudes, and there's one that'll be dominant for us. And recognizing what it is and knowing what the antidote is, I think is really important. And so maybe we'll add that on. So we'll do cross country and some miscellaneous topics, and then that will conclude the series. And I think we'll try to finish that next Wednesday, if that works for you, Casey and Jeff.
That's
And
good.
yep,
Thanks so much.
great.
Good work.
So,
Jeff.
if there's nothing else, I'll say goodnight to everybody, and thanks so much for joining, especially Casey and Jeff for giving these wonderful presentations. I think we're putting together a really good presentation that will help glider pilots for a long time if they can find it on our YouTube channel. And as it turns out, there's a lot of, I mean, I'm surprised at how many hits we're getting. It's like I didn't know there were that many people really that interested in this, but that's great. And so at any rate, good night, everyone. And we'll see you next week. We'll either see you at the field, in the case of Jeff and Eric, certainly. And if not, we'll see y'all next Wednesday. Good night, everyone.
Thank you.
Good night.
you.
Excellent presentation.